Tonight, we begin at the edge of something familiar, and yet something deeply misunderstood. For most of human history, the night sky has felt like a distant ceiling, stars scattered across darkness, unreachable and silent. But over time, we began to realize that our sun is not just a glowing disk in the sky. It is a force, a presence, a source of influence that stretches far beyond the planets we can see. And for a long time, we believed we understood where that influence ended. We thought we knew the boundary of our cosmic home. But in 1977, something quietly set out to challenge that belief. That year, 2 spacecraft left Earth. They were not built to rewrite textbooks or redefine our understanding of space. They were designed for something far simpler: a 5-year mission. A brief journey to study the outer planets, Jupiter and Saturn, and then, as their power faded, to drift silently into the dark. They were called Voyager 1 and Voyager 2. At the time, no one imagined they would still be operating nearly half a century later. No one expected that these machines, built with 1970s technology, would travel farther than any human-made object in history. And certainly, no one expected that their most important discoveries would come not from the planets, but from the empty space beyond them. Today, both Voyagers are still moving outward. Billion by billion of miles, they continue their slow journey into the unknown. Their signals, faint and fragile, take nearly a full day to reach Earth. And yet, even now, they are still sending us information, whispers from the farthest frontier we have ever reached. But what they found out there was not what anyone expected. As the Voyagers approached what scientists believed to be the edge of the solar system, something strange began to happen. The boundary wasn't where it was supposed to be. For decades, models had predicted that the sun's influence would end at a certain distance, somewhere around 90 to 100 astronomical units from the sun. That's about 8 to 9 billion miles. A vast distance, yes, but one that scientists felt confident about. And yet, when Voyager 1 arrived, it didn't find the edge there. It kept going, and going, and going. The boundary was not just slightly off. It was billions of miles farther out than expected. Over 2 billion miles beyond the predicted location. A difference so large that it couldn't be dismissed as a simple error. It meant something deeper was wrong. But distance was only the beginning. As the Voyagers continued their journey, they revealed that the very shape of this boundary, the invisible bubble surrounding our solar system, was not what scientists had imagined. For years, we pictured it as something smooth, symmetrical, like a sphere gently enclosing the sun and its planets, maybe slightly stretched, like a comet's tail, but still orderly, predictable. Instead, the data told a different story. The heliosphere, the vast region shaped by the solar wind, was distorted, compressed in some directions, extended in others, more like a bullet cutting through space than a perfect sphere. Why? Because our solar system is not standing still. It is moving. At nearly 500,000 miles per hour, the sun is traveling through the galaxy, pushing against the thin gas between the stars. From our perspective, space may feel empty and still, but on a cosmic scale, it behaves more like a flowing medium, something the solar system must move through. And that motion changes everything. Imagine a boat moving through water. At the front, the water is compressed. At the sides, it flows outward. Behind it, a wake stretches into the distance. Now imagine the sun as that boat. The heliosphere becomes its wake. Already the simple picture we once held begins to dissolve. But the surprises didn't stop there. As Voyager approached the boundary, scientists expected to see a clear transition, a kind of cosmic border crossing, a moment when the influence of the sun would suddenly give way to the environment of interstellar space. They expected solar particles to drop sharply, cosmic radiation from the galaxy to increase, and the magnetic field, the invisible structure guiding charged particles, to shift direction in a noticeable way. A clean break, a line in the sand. But that's not what happened. Instead, the transition was messy, gradual, confusing. At times, the spacecraft seemed to move in and out of the boundary, as if the edge itself were shifting. Solar particles would fade, then return. Cosmic radiation would rise, but not all at once. The magnetic field behaved in ways that didn't match predictions. It was as if the boundary wasn't a fixed wall at all. It was something alive, something dynamic, something that responded to changes in the sun itself. And perhaps most unsettling of all, when Voyager finally crossed into interstellar space, the environment beyond did not behave the way our models had predicted. The density of particles was different. The temperature was different. Even the magnetic field, expected to change direction dramatically, remained strangely aligned. It was as if the universe had quietly rewritten the rules without telling us. So what does it mean when one of the most carefully modeled regions of space, our own cosmic neighborhood, turns out to be so different from what we expected? What else might we be misunderstanding? And if we struggle to define the boundary of our own solar system, how much harder is it to imagine traveling beyond it? Because this is where the story begins to shift. Tonight, we're not just following two spacecraft drifting into the dark. We're witnessing a moment in human history when certainty gave way to curiosity, when models met reality, and reality refused to fit. When we realized that even the edge of our own home in the universe is far more complex, more dynamic, and more mysterious than we ever imagined. And as we begin to think about traveling vast distances, distances measured not in miles, but in light years, we must first confront a simple truth. We are only just beginning to understand the space we already occupy. Because before we can ask how long it would take to travel 1 light year, we need to understand what lies between here and there. But before we can understand what Voyager discovered, we need to understand what scientists thought they would find. To understand how far humanity would need to travel to cross even a single light year, we first have to understand something much closer. Not the planets, not the asteroids, not even the distant icy edges of the Kuiper Belt, but something far larger and far less visible. We have to understand the true reach of the sun. Because the sun is not just a source of light and warmth. It is not simply a glowing sphere at the center of our system. It is constantly expanding its presence outward in a way that is almost impossible to see, but impossible to ignore. At every moment, the sun is shedding itself. From its outer atmosphere, a continuous stream of charged particles flows into space. This stream is known as the solar wind, It is made mostly of protons and electrons, tiny pieces of atoms that have been energized to the point where they break free and escape the sun's gravity. These particles don't drift slowly. They rush outward at incredible speeds, hundreds of kilometers per second. Faster than any storm on Earth. Faster than any aircraft ever built. Faster even than most spacecraft we have launched. And they never stop. Every second, the sun releases millions of tons of this material into space. It spreads in all directions, filling the solar system with an invisible flow of energy and motion. If you could see it, it would not look calm. It would look like a storm. A constant, expanding storm that surrounds everything, from Mercury to Neptune, and far beyond. Over time, this outward flow creates something extraordinary. A vast region in space shaped entirely by the sun. This region is called the heliosphere. You can think of it as a kind of cosmic atmosphere, not made of air, but of plasma, not bound to a planet, but centered on a star. It is the domain where the sun's influence dominates, where its particles and magnetic fields shape the environment around us. And it is enormous. To understand just how large it is, imagine the distance from Earth to the Sun, about 93 million miles. Now stretch that distance outward, not once, not 10 times, but more than 100 times. Even then, you are only beginning to approach the outer limits of this invisible structure. Everything inside this region, from the planets to the smallest grains of dust, is immersed in the solar wind, protected by it, shaped by it. But this expansion cannot continue forever, because space, despite how empty it seems, is not truly empty. Between the stars, there is still matter, extremely thin, almost unimaginably sparse, but present. This is the interstellar medium, a faint mixture of gas and particles that fills the galaxy. Compared to Earth's atmosphere, it is almost nothing, a vacuum so perfect that we struggle to recreate it even in our most advanced laboratories. And yet, over vast distances, even this thin presence has pressure. It has motion. It has force. And eventually, it pushes back. As the solar wind expands outward, it begins to encounter this interstellar medium. And at some point, the pressure from outside balances the pressure from within. This is where the structure of the heliosphere begins to take shape. The first major boundary is called the termination shock. Up to this point, the solar wind is moving faster than the speed at which disturbances can travel through it. In simple terms, it is moving too fast to feel resistance. But when it reaches this region, it suddenly slows down. It is like a supersonic jet hitting a wall of air and forming a shock wave. The solar wind compresses, heats up, and becomes more turbulent. The smooth outward flow gives way to something more chaotic. This is not the edge of the solar system. It is only the beginning of the transition. Beyond the termination shock lies a vast, turbulent region known as the heliosheath. Here, the solar wind has slowed, but it has not stopped. It continues to move outward, but now it begins to swirl and mix, reacting to the pressure of the interstellar medium pressing inward. This region is not quiet. It is filled with magnetic disturbances, irregular flows, and energetic particles. It is a kind of boundary layer, a place where two enormous forces are interacting, but not yet fully separated. If the heliosphere is a bubble, then the heliosheath is the thick, unstable surface of that bubble. And beyond it lies the true boundary, the heliopause. This is the point where the solar wind can no longer push outward, where the influence of the sun gives way to the influence of the galaxy, where the particles streaming from our star are finally stopped by the pressure of interstellar space. If we return to our earlier analogy, the heliosphere is like a bubble drifting through a vast cosmic ocean, and the heliopause is its surface, a thin, shifting boundary between two invisible worlds. On one side, space is shaped by the sun, its magnetic field, its particles, its energy. On the other, space is shaped by the galaxy itself. It is difficult to imagine just how profound this boundary is, because unlike borders on Earth, it is not something you can see. There is no line, no wall, no sudden visual change. And yet, crossing it means leaving the environment created by our star and entering the wider universe. So where is this boundary? How far away is the true edge of the sun's influence? For decades, scientists believed they knew the answer. Based on models of the solar wind and estimates of the interstellar medium, they predicted that the heliopause would lie somewhere between 90 and 100 astronomical units from the sun. That is roughly 8 to 9 billion miles. An enormous distance by human standards, but a number that felt precise, measured, understood. They believed the heliosphere was relatively smooth, roughly spherical, maybe slightly stretched in one direction like a comet's tail, but otherwise predictable. They believed the transition across the heliopause would be clear and relatively quick. As a spacecraft crossed this boundary, they expected to see solar particles suddenly drop, galactic cosmic rays increase, and the magnetic field shift direction, marking the transition from solar space to interstellar space. A clean crossing, a definable edge, a place where we could say with confidence, here is where the solar system ends. But there is a quiet assumption hidden in all of this, an assumption that the universe behaves in ways we can easily simplify, that boundaries are clean, that structures are stable, that if we understand the forces involved, we can predict the outcome with confidence. And for a long time, that assumption seemed reasonable, until we tried to measure it, until we sent something far enough to test it. Because imagining the edge of the solar system is one thing, reaching it is something else entirely. And as we begin to think about traveling distances as vast as a light year, this boundary becomes more than just a scientific concept. It becomes the first true horizon, the first layer of space we must cross if we ever hope to leave our sun behind. But how accurate were those predictions? How close were our models to reality? And what happens when theory meets the quiet, unfiltered truth of deep space? And once scientists believed they understood this boundary, they began to predict exactly where Voyager would find it. If we want to understand how long it might take humanity to travel 1 light year, we first need to face a quieter, more immediate question. How far is the edge of our own solar system? Not in abstract terms, not as a number written in a textbook, but in a way we can actually feel. Because distance in space has a strange way of losing meaning. Numbers grow so large that they stop connecting to our everyday experience. Millions becomes billions, billions become trillions, and somewhere along the way, scale turns into silence. So let's begin somewhere familiar. The distance between the Earth and the Sun is about 93 million miles. This distance is so important that astronomers gave it a name, 1 astronomical unit, or simply 1 AU. It's a kind of cosmic measuring stick, a baseline, a way to describe the solar system in units that relate back to our home. From this perspective, Earth orbits at 1 astronomical unit.
Mars is about 1.5 astronomical units away. Jupiter, the largest planet in our solar system,
orbits at roughly 5 astronomical units. Saturn sits at about 9.5 astronomical units, and Neptune, the outermost major planet, drifts at around 30 astronomical units from the Sun. Already the distances are difficult to grasp. Neptune is 30 times farther from the Sun than Earth is. Light from the Sun takes more than 4 hours to reach it. A journey that sunlight completes in 8 minutes near Earth becomes a slow, distant glow at the outer planets. And yet, even Neptune is not close to the edge, not even remotely close. For many years, scientists believed that the boundary of the Sun's influence, the heliopause, would lie somewhere between 90 and 100 astronomical units. That means 3 times farther than Neptune. If Earth is 1 step away from the Sun, then Neptune is 30 steps away. And the edge of the solar system would be nearly 100 steps out into the dark. But even that comparison is too gentle. Let's return to miles. At 1 astronomical unit, we have 93 million miles. At 100 astronomical units, we are looking at roughly 9.3 billion miles. 9 billion miles. It is a number so large that it almost resists imagination. If you were to travel that distance in a commercial airplane, moving at around 500 miles per hour without ever stopping, it would take over 2,000 years to get there. 2,000 years, just to reach the place where scientists once believed the Sun's influence ended. And yet, even that doesn't fully capture it. Because space is not filled with landmarks. There are no roads, no signs, no sense of progression. Between the orbit of Neptune and the outer edge of the heliosphere lies an immense region of darkness, sparse, quiet, almost completely empty. If you were there, drifting between worlds, the Sun would no longer dominate the sky. It would shrink into a bright star among many. The planets would be far behind you, and still, you would not yet be at the edge. This is where our intuition begins to fail us. We tend to think of the solar system as something defined by the planets. Mercury, Venus, Earth, Mars, out to Jupiter, Saturn, Uranus, and Neptune. These are the worlds we learn about, the ones we map, the ones we imagine. But they are not the boundary. They are not even close. In truth, the planets exist deep inside the Sun's domain. They are like islands near the center of a vast ocean, while the shoreline lies far beyond the horizon. The planets we're familiar with don't define the edge of the solar system. They exist deep inside it. And beyond them, there is still so much more. Beyond Neptune lies the Kuiper Belt, a region filled with icy remnants from the early solar system. Objects like Pluto, drifting in cold, distant orbits. Farther still, possibly tens of thousands of astronomical units away, lies the hypothetical Oort cloud, a vast spherical shell of cometary material that may represent the outermost gravitational influence of the Sun. But even these regions are not what we are focusing on here, because the heliosphere, the Sun's true sphere of influence, is not defined by gravity alone. It is defined by the reach of the solar wind. And that boundary, the heliopause, was once believed to be within reach of our measurements, within reach of our understanding, within reach of Voyager. Let's consider Voyager's journey. Voyager 1, the faster of the 2 spacecraft, has been traveling for nearly half a century. It moves at about 38,000 miles per hour, faster than any human has ever traveled, faster than any spacecraft designed for exploration in its time. And yet, even at that speed, it took decades to approach the edge of the heliosphere. Decades, just to leave the sun's immediate influence. To put this into perspective, Voyager has traveled over 14 billion miles from Earth. It is the most distant human-made object ever created. And still, when it crossed into interstellar space, it had only just passed beyond the sun's boundary. 1 light year, the distance light travels in a single year, is about 5.9 trillion miles. That means Voyager has not even traveled 1% of a light year. Not even a fraction of 1%. All of this time, all of this distance, and we are still incredibly close to home by cosmic standards. So when we ask how long it would take humanity to travel 1 light year, we are not asking about a slightly longer version of Voyager's journey. We are asking about something entirely different, something vastly more extreme. Because before we can even think about reaching the stars, we must first cross the boundary of our own solar system. And that boundary, once thought to be simple and well understood, already stretches billions of miles farther than our everyday intuition can handle. It raises a quiet but profound question. If it takes decades for our fastest spacecraft to reach the edge of the sun's influence, what does that say about our place in the universe? Are we explorers standing at the edge of a vast ocean? Or are we still, in many ways, standing at the shore, just beginning to understand how deep the water really is? Because the story of distance in space is not just about numbers. It is about perspective. It is about realizing that even the space we call our own is far larger, far more complex, and far more distant than we once imagined. And yet, there is something even more remarkable about this story. Because these journeys, these incredible distances, were not originally meant to be explored at all. Voyager was never designed to reach the edge of the solar system. It was never meant to travel this far. It was built for something much simpler, and somehow it kept going. But the story becomes even more remarkable when we remember what Voyager was actually built to do. In the summer of 1977, something quietly extraordinary began. There was no sense at the time that history was being rewritten, no expectation that humanity was about to send its first true ambassadors into the depths between the stars. What unfolded instead felt, on the surface, like a well-planned scientific mission, ambitious, certainly, but still grounded in the limits of its time. 2 spacecraft stood ready on launch pads, shaped by decades of engineering, driven by curiosity, and guided by a rare opportunity written into the motion of the planets themselves. The first to depart was Voyager 2. On August 20th, 1977, it rose from Cape Canaveral, carried upward by fire and precision, leaving Earth behind with a trajectory carefully calculated years in advance. Just weeks later, on September 5th, Voyager 1 followed, despite its name, launched second, but destined to arrive first. The naming would always reflect destination, not origin. At that moment, these spacecraft were not symbols of eternity. They were tools, instruments built to answer specific questions about the outer planets, Jupiter and Saturn, the giants of our solar system. Their mission was clear: travel outward, study these distant worlds, collect data for a few short years, and then fall silent. Because in the 1970s, no one expected a spacecraft to survive indefinitely. Power sources would fade, systems would degrade, the cold of deep space would eventually claim even the most carefully engineered machine. 5 years. That was the plan. 5 years to glimpse the outer planets. 5 years to expand our understanding. 5 years, and then the journey would end. But there was something else, something almost poetic, woven into the timing of their launch. A rare alignment of planets. Once every 176 years, the outer planets, Jupiter, Saturn, Uranus, and Neptune, arrange themselves in such a way that a spacecraft can visit them one after another, using their gravity as stepping stones. It is known as the Grand Tour. Imagine trying to visit 4 distant cities, not by carrying enough fuel to reach each one, but by using the gravity of each city itself to accelerate you toward the next. That is what NASA planned. As Voyager passed Jupiter, it would be pulled forward, gaining speed. Then Saturn would do the same. If conditions allowed, it could continue onward to Uranus and Neptune, each encounter adding energy, extending the journey, pushing the spacecraft farther than any rocket alone could achieve. This alignment was not just convenient, it was rare, a window that would not open again for nearly 2 centuries. And so, in 1977, humanity took its chance. Voyager 1 sped ahead on a faster trajectory, aimed to reach Jupiter first. Voyager 2 followed a slightly slower path, but one that allowed it to continue onward to Uranus and Neptune. Together, they formed a kind of dual expedition. 2 travelers, leaving the inner solar system behind. 2 machines, moving outward into regions no spacecraft had ever explored. When Voyager 1 reached Jupiter in 1979, it transformed our understanding of the planet. The swirling clouds revealed new complexity. Storms larger than Earth itself moved through its atmosphere. Lightning flashed across alien skies. And perhaps most surprising of all, its moon, Io, was found to be volcanically active. The first time active volcanoes had been observed beyond Earth. It was as if the solar system had suddenly become more alive than we imagined. Voyager 2 followed, confirming and expanding these discoveries, then continued onward. Saturn revealed its intricate rings in unprecedented detail. Uranus, tilted on its side, rotated like a rolling sphere through space. Neptune, distant and cold, showed storms and winds stronger than anything seen closer to the sun. With each encounter, the Voyagers delivered more than expected. They did not simply observe, they revealed. And yet, even as these discoveries unfolded, the original mission was quietly coming to an end. The primary objectives had been achieved, the planets had been visited, the data had been sent. By all reasonable measures, the mission was complete. What remained was not a new phase of exploration, but a slow fading into silence. The spacecraft would continue drifting outward, their power gradually declining, their instruments shutting down one by one. Eventually, their signals would disappear, and they would become relics, artifacts of a brief moment in human history. Or at least, that is what was expected. But something remarkable happened. The Voyagers did not fall silent. They kept going. Year after year, they continued to send back data. Decade after decade, they remained alive. Their power sources, based on the slow decay of radioactive material, declined steadily, but not quickly enough to end the mission. Engineers adapted. Instruments were turned off to conserve energy. Systems were reconfigured. Software, written in an earlier era of computing, was updated from across billions of miles. Commands sent from Earth would take nearly a full day to arrive. Responses would take another day to return. And yet, communication continued. The spacecraft endured. And as they moved farther from the sun, something unexpected began to emerge. Beyond the planets, beyond the familiar regions of the solar system, the Voyagers entered a domain that had never been explored directly. A place where theory had long existed, but measurement had not. The outer boundary of the sun's influence, the edge of the heliosphere. And it was here, far beyond the original mission, far beyond the expectations of their creators, that the Voyagers began to do something extraordinary. They began to answer questions no one had originally asked. What does it feel like to leave the sun behind? Where does the solar system truly end? What lies just beyond it? These were not the questions that defined the mission in 1977, but they became the questions that defined its legacy. There is something deeply humbling about this. Two machines, built with limited memory, launched in an era before personal computers, before the internet, before the digital world we now take for granted, continuing to explore regions of space that no modern spacecraft has yet reached. They were never meant to last this long. They were never meant to go this far. And yet, through a combination of careful design, human ingenuity, and a kind of quiet persistence, they became something more. They became the first objects to carry human presence to the threshold of interstellar space. And as we consider the idea of traveling 1 light year, a distance so vast that it dwarfs even the achievements of Voyager, we begin to see this journey in a different light. Because before we can imagine crossing the space between stars, we must first understand the journey that has already begun. A journey that started not with a grand ambition to reach interstellar space, but with a simple mission to visit a few distant planets. And somehow, that was enough. Enough to begin a path that would extend far beyond its original purpose. Enough to carry humanity, in some small way, beyond the edge of its own solar system. There is a quiet lesson here. Sometimes, the most profound discoveries are not the ones we set out to find. They are the ones we encounter when we keep going, just a little farther than we planned. And to truly understand how extraordinary those discoveries are, to appreciate what Voyager revealed about the edge of our solar system, we need to look more closely at the machines themselves, how they were built, how they survived, and how something so simple managed to travel so far. To understand how extraordinary Voyager's discoveries really are, we need to look at the machines themselves. There is something quietly astonishing about Voyager. Not just where it has gone, but what it is. Because when we imagine a spacecraft traveling billions of miles into deep space, crossing the boundary of the solar system and entering the vast darkness between the stars, we tend to picture something advanced, something sleek, something built with the most powerful technology humanity has ever created. But Voyager is none of those things. In fact, by today's standards, it is almost impossibly simple. Its computers are not measured in gigabytes or even megabytes, but in kilobytes. Each Voyager spacecraft carries 3 onboard computer systems. Together, they hold roughly 68 kilobytes of memory. 68,000 bytes. To put that into perspective, a single photo taken on a modern smartphone is often thousands of times larger than that entire system. The device in your pocket, something you might use to check the time or scroll through messages, is millions of times more powerful than the computers guiding Voyager through interstellar space. And yet, your phone has never left Earth. Voyager has left the solar system. There is a quiet irony in that contrast. Your phone is millions of times more powerful, and yet it's Voyager that reached interstellar space. But power alone is not what defines a machine's purpose. Voyager was not built to be powerful. It was built to be reliable. Its systems were designed in an era before personal computers, before the internet,
before the digital world became woven into everyday life. Engineers relied on simplicity, redundancy, and careful planning. Every function had to work not just once, but for years, without the possibility of repair.
Because once Voyager left Earth, there would be no way to reach it again. No maintenance, no upgrades, no second chances. And yet, somehow, it continues to function. The spacecraft operates through 3 primary computer systems, each responsible for a different task. One manages commands from Earth, another processes scientific data. The third controls the spacecraft's orientation, ensuring its antenna remains pointed back toward our distant planet. These systems work together in a delicate balance, maintaining stability as Voyager drifts through space at tens of thousands of miles per hour. But perhaps even more remarkable than its computing power is its communication. Voyager does not send signals the way we imagine modern systems might. There are no high-speed transmissions, no streaming data, no constant connection. Instead, it whispers. Its transmitter operates at about 23 watts of power, less than a typical household light bulb. That signal then travels across billions of miles, spreading outward into space, weakening with every passing second. By the time it reaches Earth, it is unimaginably faint. So faint that detecting it requires some of the most sensitive instruments ever built. Massive radio antennas, hundreds of feet wide, forming part of NASA's deep space network. Even then, the signal is barely there. A tiny ripple in a vast ocean of cosmic noise. And time itself becomes part of the conversation. When engineers send a command to Voyager, it does not respond immediately. It cannot. At such distances, even light, the fastest thing in the universe, moves slowly. A signal sent from Earth takes more than 18 hours to reach Voyager 2. For Voyager 1, it can take over 22 hours. Then, after the command is received, Voyager responds. And that signal takes another 18 to 22 hours to return. A simple exchange, question and answer, can take nearly 2 days. Imagine trying to fix a problem on a machine when every step of communication takes 48 hours. Imagine debugging software written half a century ago, on hardware you cannot touch, at a distance measured in billions of miles. And yet, engineers continue to do exactly that. Over the years, they have updated Voyager's software. They have reconfigured its systems. They have even revived components that had not been used for decades. In one instance, thrusters that had remained dormant for nearly 40 years were successfully reactivated, responding perfectly, as if no time had passed at all. It is as if the spacecraft exists outside of time, a relic of another era, still performing its function with quiet precision. But no machine can run forever. Voyager is powered by something both elegant and finite. Radioisotope thermoelectric generators, or RTGs. Inside these generators is a material called plutonium-238. As it naturally decays, it produces heat. That heat is then converted into electricity, providing a steady source of power for the spacecraft. At launch, each Voyager generated about 470 watts of power. But radioactive decay is a slow, unstoppable process. Year by year, the power output decreases. A few watts at a time. Not dramatic, not sudden, but constant. And over decades, those small losses begin to matter. Engineers have had to make difficult choices. Instruments have been turned off. Heaters have been shut down. Systems have been carefully managed, prioritizing the most important functions, while letting others fade into silence. The cameras, which once captured stunning images of Jupiter and Saturn, were turned off decades ago. Not because they stopped working, but because there was no longer enough power to keep them running. And still, Voyager continues.
Even now it sends back data, tiny streams of information, traveling across unimaginable distances, telling us about a region of space we have never directly experienced before. There is something deeply human about this. A machine built with limited resources, operating far beyond its intended lifespan, adapting, enduring, continuing its journey long after expectations have faded. It is not correct, it is not powerful, but it is persistent. And perhaps that is what matters most. Because when we think about traveling 1 light year, a distance so vast that even Voyager's journey feels small in comparison, we often focus on speed, on propulsion, on how fast we can go. But Voyager reminds us that endurance may be just as important. The ability to survive, to function, to keep going, even as conditions change and systems begin to fail. Because space is not just far, it is unforgiving, cold beyond imagination, silent beyond comprehension. And yet, this small machine, built decades ago, continues to move through it. A faint signal in the dark, a reminder that exploration is not always about reaching the destination quickly. Sometimes, it is about staying on the journey long enough to see what lies beyond. And as Voyager drifts farther and farther from the sun, carrying with it the last whispers of human engineering from another era, it approaches something profound. Not just a physical boundary, but a conceptual one. The edge of what we thought we understood. Because with this fragile, decades-old technology, humanity has come closer than ever to crossing into the unknown. And with that crossing, something unexpected begins to unfold. Because as Voyager approached the boundary of the solar system, it did not find what scientists had predicted. And with this fragile, decades-old technology, humanity approached a boundary it believed it had already mapped. Before Voyager ever reached the edge of the solar system, that edge already existed in the human mind. It had been calculated, simulated, refined, and debated for decades. Scientists had built models not from imagination alone, but from physics. Equations that described how particles move, how pressure behaves, how magnetic fields shape space itself. And from those models, a picture emerged, clear, structured, logical. A boundary that could be understood, a boundary that could be predicted. At the center of this picture was the solar wind, the steady stream of charged particles flowing outward from the sun. Scientists knew its speed, roughly hundreds of kilometers per second. They knew its density near Earth. They knew how it behaved over time. And they knew that eventually, this outward flow had to encounter something. Because the galaxy is not empty. Even in the vast darkness between stars, there is matter, thin, almost impossibly sparse, but still present. The interstellar medium presses gently inward, while the solar wind pushes outward. Somewhere, those two forces must meet. And where they meet, a boundary must form. The question was not whether the boundary existed. The question was where, and what it looked like. By the late 20th century, scientists had developed increasingly sophisticated models of this region. They used computer simulations to recreate the interaction between the solar wind and the interstellar medium. They included plasma behavior, magnetic fields, and the motion of the sun through the galaxy. And again, the models pointed to a similar structure. The first major boundary was expected to be the termination shock. Here, the solar wind, moving faster than the speed at which disturbances travel through plasma, would suddenly slow down. Like a supersonic jet creating a shockwave in the air, the solar wind would compress, heat up, and become turbulent. Based on calculations, this region was predicted to lie somewhere between 75 and 90 astronomical units from the Sun, far beyond Neptune, but still within a range that seemed reasonable. Beyond this shock, the solar wind would enter the heliosheath, a transitional region, perhaps 10 to 20 astronomical units thick, where the slowed plasma would continue to move outward, but in a more chaotic and irregular way. The flow would become turbulent, bending and shifting under the pressure of the interstellar medium. This region was expected to be complex, but understandable. A buffer zone, a place where solar space gradually gave way to interstellar space. And then, beyond it, lay the final boundary, the heliopause. This was the point where the outward pressure of the solar wind would be balanced by the inward pressure of the interstellar medium, where the Sun's influence would effectively end, where the environment would shift from solar-dominated to galaxy-dominated. The predicted distance? Somewhere between 90 and 100 astronomical units, roughly 9 billion miles from the Sun. This number appeared again and again in simulations. It was not exact, but it was consistent. It felt right. And perhaps more importantly, the structure of this boundary seemed intuitive. Scientists imagined the heliosphere as a kind of bubble, not perfectly spherical, perhaps slightly stretched in the direction opposite the Sun's motion through the galaxy, but still smooth, still continuous, still predictable. The kind of structure that physics often produces, elegant, balanced. And within this model, the transition across the heliopause was expected to be clear. If a spacecraft were to cross it, the signs would be unmistakable. First, the solar wind particles, those streaming outward from the Sun, would drop sharply. Their density would fall, perhaps almost to zero. At the same time, cosmic rays, high-energy particles originating from distant supernovae and other violent events in the galaxy, would increase. Inside the heliosphere, these cosmic rays are partially shielded by the Sun's magnetic field. But beyond the heliopause, that shielding disappears. So the transition should be obvious: a drop in solar particles, a rise in cosmic radiation, a clear signal that the spacecraft had left the Sun's domain. And then, perhaps most importantly, there was the magnetic field. Inside the heliosphere, the Sun's magnetic field dominates. It flows outward, shaped by the rotation of the Sun and the movement of the solar wind. But outside, in interstellar space, the magnetic field is shaped by the galaxy itself. The orientation should be different. So when a spacecraft crossed the heliopause, scientists expected to see a rotation in the magnetic field direction. Not necessarily a dramatic flip, but a measurable shift. A change that would mark the crossing of an invisible boundary. In other words, the heliopause was not just a distance, it was a signature, a set of changes that, together, would define the edge of the solar system. And scientists felt confident in this picture, not because it was simple, but because it was grounded in well-understood physics, the behavior of plasma, the dynamics of shock waves, the interaction between magnetic fields and charged particles. These were not unknown concepts. They had been studied for decades, both in laboratories and through observations within the solar system. Of course, there were uncertainties. The exact distance might vary depending on solar activity. The shape might not be perfectly uniform. The interstellar medium might not be completely consistent in all directions. But the overall structure, the existence of the termination shock, the heliosheath, and the heliopause seemed solid. reliable, predictable. If anything, the models might be off by a few astronomical units, a small adjustment, a minor correction, nothing that would fundamentally change the picture. And so, as Voyager moved outward, scientists waited. They expected the spacecraft to encounter the termination shock somewhere around 80 astronomical units. They expected it to spend several years crossing the heliosheath, and then, around 100 astronomical units, they expected it to reach the heliopause. A clean transition, a clear boundary, a moment when theory would be confirmed by observation. There is a certain comfort in this kind of expectation, a sense that the universe, while vast and complex, still follows patterns we can understand, that with enough data, enough equations, enough careful thinking, we can map even the most distant regions of our cosmic home. But there is also a quiet risk, because when we begin to feel certain, we begin to assume that reality will behave the way we expect it to, that boundaries will be where we predict, that transitions will be clean, that the universe will follow the lines we have drawn for it. And sometimes it does. But sometimes it doesn't. Because models are not reality. They are approximations. They are our best attempts to describe something we cannot yet fully observe. And when observation finally arrives, when a spacecraft actually travels into that distant region and begins to measure it directly, something important happens. The model is tested, and reality has the final word. So what happens when the data doesn't match the prediction? What happens when the boundary is not where we thought it would be? When the transition is not clean? When the structure itself begins to behave in ways we did not anticipate? These are not just small corrections. These are moments when understanding shifts, when confidence gives way to curiosity, when the universe reminds us that it is always more complex than our descriptions of it. And that is exactly what Voyager encountered. Because when it finally approached the edge of the solar system, almost every expectation began to unravel. The distances were wrong, the shape was wrong, the behavior was wrong, and even the very idea of a clear boundary began to dissolve. But when Voyager arrived, almost every one of these expectations began to fail. For decades, the edge of the solar system existed as a prediction, a number, a boundary drawn not by direct experience, but by equations, carefully constructed, widely accepted, and quietly trusted. Somewhere between 90 and 100 astronomical units from the Sun. That was where scientists believed the heliopause would be, the place where the solar wind would finally yield to the interstellar medium, the place where the Sun's influence would fade and the galaxy would begin. It was not a guess, it was a conclusion, and for a long time, it felt like a solid one. So, as Voyager moved outward, past the planets, beyond Neptune, through the deepening silence of the outer solar system, scientists waited for confirmation. They expected a moment, a crossing, a clear signal that the spacecraft had reached the boundary they had long imagined. But that moment did not come, at least, not when it was supposed to. Voyager 1 passed 90 astronomical units, then 100. And still, it had not reached the edge. The solar wind was still present. The transition had not occurred. So Voyager continued, slowly, steadily, drifting farther into the dark. At 110 astronomical units, still no boundary. At 115 astronomical units, still nothing definitive. The spacecraft had already traveled billions of miles beyond where the heliopause was supposed to be. And then, finally, at around 121 astronomical units from the Sun, something changed. The solar particles dropped. Cosmic rays surged. The data shifted in a way that could no longer be ignored. Voyager had crossed into interstellar space. But by then, something was already clear. The prediction had not just been slightly off. It had been wrong by an enormous margin. More than 2 billion miles farther than expected. A difference so large that it forced scientists to reconsider not just the numbers, but the assumptions behind them. Because this wasn't a rounding error. This wasn't a small correction. This was a sign that something deeper in the model did not reflect reality. The map wasn't slightly wrong. It was fundamentally misleading. And yet, even that was only the beginning. Because once scientists began to compare data from both Voyager 1 and Voyager 2, another pattern began to emerge. The heliosphere was not shaped the way they had imagined. For years, the dominant image had been simple, a sphere, or perhaps a slightly stretched sphere, like a comet with a gentle tail. Something symmetrical, balanced, predictable. But space, as it often does, had something else in mind. The data revealed that the heliosphere is not evenly shaped at all. It is compressed in some directions, extended in others, distorted by forces that had been underestimated. Rather than a smooth bubble, it behaves more like a compressed, asymmetric structure, often described as a bullet or a teardrop, blunt at the front, stretched at the back, uneven along its sides. And to understand why, we have to step back and imagine something we rarely consider. The Sun is not standing still. It is moving. Our entire solar system is traveling through the galaxy at incredible speed, around 490,000 miles per hour. We are orbiting the center of the Milky Way, carried along through a vast sea of interstellar gas and magnetic fields. We do not feel this motion. There is no wind, no resistance we can sense. But on a cosmic scale, it matters. Because as the Sun moves forward, it pushes against the interstellar medium, and that medium pushes back. Imagine again a boat moving through water. At the front, the water compresses, building pressure. At the sides, it flows around the hull. Behind the boat, a wake forms, stretching outward into the distance. Now replace the boat with the Sun. Replace water with the thin gas between the stars, and replace the wake with the heliosphere. Suddenly, the shape begins to make sense. The front of the heliosphere, the direction the Sun is moving, is compressed. The solar wind has less space to expand before it meets resistance. The sides are distorted, influenced by local variations in the interstellar medium, and the rear stretches outward, forming a long tail that may extend for hundreds of astronomical units. This is not a static structure. It is dynamic, shaped continuously by motion, pressure, and interaction. And this realization changes something fundamental. Because if the heliosphere is not symmetric, then the distance to its boundary is not the same in every direction. Voyager 1 and Voyager 2 are not traveling along identical paths. They are moving through different regions of this distorted structure. And that explains something curious. Voyager 1 crossed the heliopause at around 121 astronomical units. Voyager 2, traveling in a different direction, crossed at about 119 astronomical units. Close, but not identical. And that small difference carries a larger implication. The edge of the solar system is not a perfect shell surrounding us. It is uneven, variable, shaped by forces beyond our immediate control. For the first time, we were not just observing the boundary. We were beginning to understand its geometry. And with that understanding came a deeper realization. The heliosphere is not just influenced by the sun. It is shaped by the galaxy, by the density of the interstellar medium, by magnetic fields that stretch across light years, by regions of space we cannot see directly, but whose effects ripple into our own neighborhood. The boundary between the solar system and interstellar space is not just a line. It is a negotiation, a balance between two vast environments. And that balance shifts. It responds. It evolves. So what does this mean for us? What does it mean for the idea of traveling 1 light year? It means that before we even begin that journey, we must pass through a region that is far more complex than we once believed. Not a clean exit, not a simple threshold, but a dynamic, shifting frontier. A boundary that does not behave the same way in all directions. A boundary that cannot be described by a single number. And if even this first step, the edge of our own solar system, is more complicated than expected, what does that suggest about the journey beyond? How many other assumptions might break down? How many other simple models might turn out to be incomplete? Because space is not just vast, it is subtle. It resists simplification. And every time we think we have understood it, it reveals another layer of complexity. Voyager did not just show us that the heliopause was farther away than we thought. It showed us that the very idea of a neatly defined edge might not apply in the way we expected. Distance, shape, structure, none of them behaved as cleanly as our models suggested. And yet, this is only the beginning of the mystery. Because knowing where the boundary is not the same as understanding how it behaves. And as Voyager continued its journey, something even more puzzling began to emerge. Because the real mystery was not just about distance or shape, it was about behavior, about how this boundary moves, shifts, and interacts with the forces around it. Because what Voyager encountered was not a fixed edge at all. But the real mystery began not with where the boundary was, but how it behaved. If the story had ended with distance, it would have already been enough. A boundary farther than expected, a shape more complex than imagined, a reminder that even our closest cosmic environment does not behave as neatly as we once believed. But as Voyager moved closer to the edge, something even stranger began to unfold. Because the real mystery was not just where the boundary was, it was how it behaved. For years, scientists had imagined the heliopause as a kind of border, not visible, not solid, but still defined. A place where conditions would change in a clear and recognizable way, like crossing an invisible line. But as Voyager approached that line, the data began to tell a different story. The transition did not happen suddenly. It did not happen cleanly. Instead, it began slowly, almost quietly. Long before Voyager officially crossed into interstellar space, its instruments started to detect subtle changes. Cosmic rays, high-energy particles from distant parts of the galaxy, began to increase. Not sharply, not all at once, but gradually. At the same time, the particles coming from the sun, the solar wind, began to weaken. Again, not abruptly, but steadily. It was as if Voyager was entering a region where two worlds were beginning to overlap. Not yet one, not yet the other. A place
in between. And then, in 2012, something entirely unexpected appeared in the data. A structure no model had predicted. A region that would come to be known as the magnetic highway. To understand why this was so surprising, we need to think about something we cannot see, but that shapes everything in space. Magnetic fields. Both the Sun and the galaxy generate magnetic fields, vast, invisible structures that guide the motion of charged particles. These fields are not static. They twist, bend, and stretch through space, carried by moving plasma.
Inside the heliosphere, the Sun's magnetic field dominates. It extends outward, carried along by the solar wind, forming a complex spiraling structure. Beyond the heliopause, the galaxy's magnetic field takes over. And scientists expected that when Voyager crossed this boundary, it would detect a clear change in the direction of that field. But before that crossing, Voyager encountered something else. In this mysterious region, the magnetic field lines appeared to become highly organized, aligned, ordered. Instead of the tangled, chaotic structure expected in the heliosheath, the field lines formed pathways, long, extended lines stretching outward. And along these lines, particles began to move, in both directions. Solar particles, still flowing outward from the Sun, traveled along these magnetic paths. At the same time, galactic cosmic rays flowed inward, entering the heliosphere along the very same lines. It was as if a bridge had formed, a connection between two regions that was supposed to be separated. Scientists called it the magnetic highway, because in this region, particles were no longer confined to one side or the other. They could travel freely along these magnetic pathways, moving between the solar system and interstellar space. This was not something the models had predicted. The boundary was supposed to act like a barrier, a transition zone where conditions changed, not a region where they mixed so freely. And yet, here was Voyager, drifting through a place where the distinction between inside and outside was beginning to blur. Imagine standing at the edge of an ocean. You expect a shoreline, a place where land ends and water begins. But instead, you find something different. A wide, shifting region where waves wash back and forth, where currents mix, where the boundary is constantly moving. You cannot point to a single line and say, "Here it begins." That is what Voyager was experiencing. The edge of the solar system was not a fixed boundary. It was a region, a dynamic, changing environment where the influence of the Sun and the galaxy overlapped and interacted. And this region did not behave consistently. At times, Voyager seemed to move deeper into it. At other times, the boundary appeared to shift, as if responding to forces from the Sun itself. Bursts of solar activity, eruptions on the Sun's surface, send waves of energy outward through the solar wind. These waves travel for years, eventually reaching the outer edges of the heliosphere. When they arrive, they push against the boundary, causing it to expand. Later, as the energy dissipates, the boundary contracts again. It is as if the heliosphere is breathing, expanding, contracting, responding to events that occurred billions of miles away, years earlier. And Voyager, drifting slowly through this region, was caught within that motion. At one point, it even appeared to cross the boundary, and then cross back again. Not because the spacecraft reversed direction, but because the boundary itself moved. This was something entirely new. The idea that the edge of the solar system could shift enough for a spacecraft to move in and out of it without changing its own trajectory. A boundary that was not fixed in space, but alive with motion. And within this shifting region, The magnetic highway acted as a kind of doorway, a place where particles could flow freely, where the separation between solar and interstellar space became less defined. For scientists, this raised profound questions. If the boundary is not sharp, how do we define it? If particles can move across it before the actual crossing, what does it mean to be inside or outside the solar system? And perhaps more importantly, if even this boundary, so close in cosmic terms, is this complex, what does that say about the boundaries we imagine elsewhere in the universe? Because we often think of space in terms of clear divisions: solar system, interstellar space, galaxy. But Voyager was showing us that these divisions are not always clean. They are layered. They are dynamic. They are shaped by forces that interact in subtle and unpredictable ways. And as we think about traveling 1 light year, leaving the sun's influence behind and moving into the vastness between stars, this realization becomes important. The journey is not just about distance. It is about crossing environments, crossing regions where the rules begin to change, where the familiar gives way to something new. And if the very first boundary we encounter behaves like this, complex, shifting, interconnected, then the journey ahead may be far less straightforward than we imagine. The magnetic highway is a reminder of that, a reminder that space is not divided by simple lines. It is woven together by invisible structures, guiding particles, shaping motion, connecting regions that seem separate. And as Voyager moved through this region, following those invisible paths, it was not just approaching the edge of the solar system. It was entering a new kind of space. A space where definitions blur, where boundaries breathe, where the distinction between here and there begins to fade. And then, finally, something changed. The solar particles, the ones that had accompanied Voyager since its departure from Earth, began to disappear almost completely. The cosmic rays stabilized at a new, higher level. The data shifted in a way that suggested something definitive had happened. Voyager had crossed, not through a sharp line, but through a living frontier. And beyond that frontier lay something humanity had never directly measured before: the true environment between the stars. And when Voyager finally moved beyond this shifting frontier, it gave us our first direct measurements of interstellar space. For most of human history, the space between the stars was imagined as emptiness, a vast, silent void, a place where nothing exists, no air, no matter, no structure, just darkness stretching endlessly in every direction. It is an intuitive idea. After all, when we look up at the night sky, the stars appear separated by enormous gaps of blackness. Those gaps feel empty, still, almost peaceful. But as Voyager crossed the boundary of the heliosphere and entered interstellar space, something subtle and profound began to emerge. That emptiness was not empty at all, not in the way we imagined. What Voyager found was not a void, but an environment, extremely thin, extremely quiet, but still real. To understand this, we have to let go of our everyday intuition. On Earth, even the air around us feels substantial. Every breath contains trillions upon trillions of particles. The atmosphere presses against us with a weight we barely notice, yet it shapes everything, from weather to sound to life itself. Now imagine removing almost all of that, not reducing it by half, not by 1,000 times, but by factors so extreme they are difficult to comprehend. In interstellar space, the density of matter is incredibly low, on average, about 0.1 atoms per cubic centimeter. To compare, The air you are breathing right now contains around 10 trillion atoms per cubic centimeter. That means interstellar space is vastly emptier than any vacuum we can create on Earth. Even our most advanced laboratory chambers cannot come close. And yet, it is not zero. There are still particles, still atoms, still matter drifting between the stars. Spread out over enormous distances, these particles form the interstellar medium, a faint, almost ghost-like presence that fills the galaxy. Voyager measured this directly. For the first time in human history, we were no longer inferring what interstellar space might be like. We were touching it. And what we found was both subtle and surprising. The density was not exactly what models predicted, slightly higher in some regions, slightly lower in others. Not dramatically different, but enough to matter. Because when you are dealing with environments this delicate, even small differences can change how boundaries behave. But density is only one part of the story. There is also pressure. On Earth, pressure is something we feel constantly, even if we are not aware of it. It is the weight of the atmosphere pressing down on us. At sea level, that pressure is about 100,000 pascals. In interstellar space, the pressure is almost unimaginably small, around a few trillionths of a pascal. It is so low that, in practical terms, it feels like nothing. And yet, it is enough. Enough to balance the outward force of the solar wind, enough to shape the boundary of the heliosphere, enough to define where the sun's influence ends. This is one of the quiet surprises of the universe. Even the faintest presence, spread across vast distances, can have real effects. Even in the emptiest regions of space, there is still structure, pressure, and motion. And then there is temperature. At first glance, this is where things become truly counterintuitive. Voyager's measurements suggest that interstellar space near our solar system has a temperature of tens of thousands of degrees, 50,000, sometimes even higher. That sounds extreme, hotter than the surface of the sun in some cases. But here, we must be careful with our definitions. Temperature, in physics, does not mean what we feel as heat. It measures the average energy of particles. In interstellar space, those particles are moving very fast, but there are so few of them that they cannot transfer much energy. If you were somehow floating in this environment, you would not feel warmth. You would freeze. Because heat requires interaction, particles colliding, transferring energy. In interstellar space, those collisions are incredibly rare. So despite the high temperature, there is almost no heat. It is a strange kind of environment. Energetic, but empty. Active, but silent. And then there is the magnetic field. Voyager's instruments revealed that interstellar space is threaded with magnetic structures, weak compared to Earth's magnetic field, but still present. These fields shape how particles move. They guide cosmic rays. They connect regions of space across vast distances. But once again, the measurements did not perfectly match expectations. The strength of the magnetic field, its direction, its variations over distance, all of these showed subtle differences from the models. Not enough to overturn our understanding, but enough to remind us that theory and reality are not always identical, even in regions we thought we understood. And perhaps that is the most important lesson of all. Interstellar space is not a blank canvas. It is not a simple void waiting to be crossed. It is a complex environment, shaped by forces we are only beginning to measure directly. It has structure, it has variation, it has behavior. And as Voyager moved deeper into this environment, it began to detect something even more dynamic. Waves. Subtle oscillations in the plasma. Ripples traveling through the interstellar medium, carrying information about density and motion. These waves allowed scientists to calculate properties of the space around Voyager with remarkable precision. And they revealed something else. Interstellar space is not uniform. Its density changes slightly over distance. Its properties vary from one region to another. It is not a single, consistent environment, but a patchwork of conditions shaped by the history of nearby stars, supernova explosions, and the movement of matter through the galaxy. So when we imagine traveling 1 light-year, we are not imagining a journey through empty nothingness. We are imagining a journey through a subtle, shifting medium, a space that resists simplicity, a space that changes as we move through it. And this has implications, because movement through interstellar space is not just about covering distance. It is about interacting with this environment, with its particles, its magnetic fields, its radiation. Even though the density is incredibly low, over long distances, millions or billions of miles, these interactions begin to matter. They influence how spacecraft travel, how radiation accumulates, how materials behave, and how we would design any future journey beyond the solar system. Because space is not just far, it is different. And the farther we go, the more those differences begin to shape the journey itself. Voyager gave us our first direct glimpse of this. A small window into a region that had always been distant, theoretical, almost abstract. And what it showed us was not emptiness, but presence. Not silence, but subtle activity. Not nothing, but something very delicate, very quiet, and very real. It is easy to overlook this, to think that because interstellar space is so thin, it does not matter. But in the vast scale of the universe, even the smallest forces can shape entire systems. Even the faintest pressure can define a boundary. Even the emptiest regions can carry structure. And as we step back and consider this delicate, almost invisible environment that fills the space between stars, we begin to see the journey ahead in a new way. Because traveling 1 light-year is not just about leaving the solar system. It is about entering this medium and moving through it for unimaginable distances. Through a space that is quiet, but not still. Empty, but not nothing. And yet, even as Voyager revealed the nature of interstellar space, it also uncovered something unexpected. Because the sun's influence did not simply stop at the heliopause. It continued, in ways no one had predicted, carrying its presence farther into the galaxy than we had ever imagined. But Voyager didn't just measure stillness. It revealed that the sun's influence extends even farther than we imagined. By the time Voyager crossed into interstellar space, it had already changed our understanding of where the solar system ends. But what it revealed next would go even further. Because leaving the sun behind did not mean leaving its influence behind. In fact, in the quiet darkness beyond the heliopause, Voyager began to detect something unexpected. Something that suggested the sun's presence still reached farther than anyone had imagined. It began with waves. Not waves in the way we experience them on Earth, no water, no sound, no visible motion, but waves in the plasma that fills interstellar space. Subtle oscillations rippling through an environment so thin that even the smallest disturbance becomes meaningful. These waves were not random. They arrived in bursts, patterns, signals that carried information about something distant. And when scientists traced those signals back, they found something remarkable.
These waves were caused by the sun. Years earlier, powerful eruptions, solar storms, known as coronal mass ejections, had blasted enormous amounts of energy into space. These bursts traveled outward through the heliosphere at high speeds, moving for years across billions of miles. Eventually, they reached the heliopause, and when they did not stop. Instead, they struck the boundary like a hammer hitting a surface. And from that impact, a new kind of wave was launched. Not in the solar wind, but into interstellar space itself. A shock wave, a ripple moving outward into the galaxy. Voyager, already beyond the heliopause, detected these waves as they passed through its instruments. It was like hearing the echo of an event that had happened years before, far closer to the sun. Scientists began to refer to them, informally, as tsunami waves, because they behaved in a similar way. A disturbance created in one region, traveling across an immense distance, carrying energy far beyond its origin. This discovery carried a quiet but profound implication. The sun's influence does not simply end at the heliopause, it continues. Not as a steady flow of particles, but as waves, as disturbances, as echoes that move through interstellar space long after the initial event has passed. It is as if the sun, even from billions of miles away, can still reach out and touch the space between the stars. And Voyager was there to feel it. But this was only the first layer of discovery. Because alongside these waves, something else began to challenge our expectations. The magnetic field. Before Voyager reached interstellar space, scientists had predicted that crossing the heliopause would involve a clear change in magnetic orientation. Inside the heliosphere, the sun's magnetic field dominates. Outside, the galaxy's field should take over. The two were expected to be different, perhaps not completely opposite, but distinct enough to measure. A rotation, a shift, a clear signal of transition. But when Voyager 1 crossed into interstellar space, something surprising happened. The magnetic field did not change in the way expected. It remained almost the same. Not identical, but aligned in a way that made the transition difficult to interpret at first. This led to confusion. Had Voyager really crossed the boundary? Or was it still within some extended region of solar influence? The answer took time to confirm, but eventually it became clear. Voyager had indeed entered interstellar space. And the reason for the lack of a strong magnetic shift was something both subtle and profound. The local interstellar magnetic field just happened to be aligned in a similar direction to the sun's field in that region. A coincidence, but a meaningful one. Because it revealed that the galaxy's magnetic structure is not uniform. It varies from place to place. It bends, it twists. It changes direction over relatively short distances, at least on cosmic scales. And then came Voyager 2. Traveling in a different direction, through a different region of space, it crossed the heliopause years later. This time, the magnetic field did change. Not dramatically, but enough to be measured. A shift of about 20 degrees. Two spacecraft. Two different paths. Two different magnetic signatures. Together, they revealed something important. The interstellar magnetic field is not a single, uniform structure. It is localized, complex, shaped by its environment. And once again, the simple models had to give way to a more detailed reality. But perhaps the most intriguing discovery came from something even more elusive. Cosmic rays. These are high-energy particles, mostly protons, that travel through the galaxy at near light speeds. They are born in violent events, supernova explosions, shock waves, and other energetic processes scattered across the Milky Way. For years, scientists had studied cosmic rays from within the heliosphere. But the sun's magnetic field acts as a shield, deflecting many of them and altering their paths. So the measurements we had were incomplete, filtered, indirect. Voyager changed that. As it moved into interstellar space, it began to measure cosmic rays directly, without the shielding effect of the heliosphere. And at first, some of the results matched expectations. The overall intensity increased. More cosmic rays were present outside the solar system than inside. But when scientists looked more closely, something unexpected appeared. The cosmic rays were not evenly distributed. They did not arrive uniformly from all directions. Instead, there were patterns. Certain directions showed higher intensities, others showed less. This was surprising. If cosmic rays were coming from all over the galaxy, one might expect them to appear relatively uniform. But they didn't. Instead, their distribution suggested something else: structure. Something in the interstellar environment was guiding them, shaping their paths. Perhaps the magnetic field was acting like a set of invisible channels, directing particles along certain routes. Perhaps nearby sources, remnants of ancient supernovae, were contributing more strongly from specific directions. Or perhaps the local region of space around our solar system is more complex than we realized. Whatever the explanation, the implication was clear. Interstellar space is not uniform. It has direction. It has variation. It has patterns that reflect deeper structures we are only beginning to understand. And taken together, these discoveries begin to form a picture, a layered, evolving understanding of the space beyond our solar system. First, we learned that the boundary was farther than expected. Then, that its shape was not simple. Then, that it behaved dynamically, shifting and interacting with solar activity. Now, we see that even beyond that boundary, space is filled with motion, with waves, with magnetic structures, with particles moving in patterns that reveal hidden complexity. This is not the empty void we once imagined. It is an active environment. Quiet, yes. Subtle, certainly. But filled with processes that unfold over vast distances and timescales. And as we begin to think about traveling 1 light year, these discoveries take on new meaning. Because such a journey is not just about covering distance. It is about moving through this environment, through waves that originate from distant stars, through magnetic fields that stretch across light years, through streams of high-energy particles that carry the history of the galaxy itself. It is about navigating a space that is not empty, but structured in ways we are only beginning to map. Voyager has shown us the first glimpse of that reality, a glimpse from just beyond our solar system. And already, the complexity is greater than expected. So what lies farther out? What happens as we move deeper into interstellar space? What new structures, new forces, new surprises might we encounter along the way? Because if even this first step beyond the sun reveals so much, then the journey of 1 light year is not just long. It is unknown. And perhaps that is what makes it so compelling. Because every layer we uncover does not simplify the universe. It reveals how much more there is to understand. So after all of this, after the shifting boundaries, the magnetic highways, the waves, the fields, and the cosmic rays, what did Voyager really change? By the time Voyager reached the edge of the solar system, it had already rewritten something important. Not just a number, not just a distance, but a mindset. Because what Voyager revealed was not simply that our models were wrong. It revealed something deeper, something more fundamental about how we understand the universe itself. For years, decades even, scientists had built a picture of the heliosphere using the best tools available: observations, theory, simulation. Every piece of knowledge was carefully assembled into a model that made sense of the data we had. And in many ways, that model worked. It correctly predicted that there would be a boundary. It correctly described the interaction between the solar wind and interstellar space. It even captured the general structure of the system, the existence of a shock, a transition region, and an outer limit. The foundation was sound, but the details were incomplete. The distance was off. The shape was more complex. The boundary was not clean. The behavior was dynamic, not static. The magnetic field did not behave as expected. The environment beyond the boundary was not quite what we had imagined. And yet, none of this means the science was wrong in the way we often think of failure. Because science does not fail when it is corrected. It evolves. It refines itself. It moves closer to reality. Science doesn't fail when it's wrong. It improves when reality corrects it. This is one of the quiet truths behind every discovery. Models are not the universe. They are our best attempts to describe it. They are maps, not the territory itself. And like all maps, they are simplified. They leave things out. They smooth over complexity. They assume patterns that may not hold in every case. But they are not useless. They are essential. Because without them, we would have no starting point, no framework, no way to make sense of what we observe. Voyager did not destroy the model of the heliosphere. It completed it. It added depth. It revealed the missing layers. And in doing so, it reminded us of something important. Understanding is not a fixed destination. It is a process, a continuous cycle. We begin with a question, we build a model, we test it, and then we adjust. Prediction, observation, correction. Again and again, this cycle repeats. And each time, our picture of the universe becomes a little more detailed, a little more accurate, a little more aligned with reality. Voyager is one of those moments in that cycle, a moment where prediction met observation, and observation reshaped prediction. But the implications of this go beyond the heliosphere. Because what Voyager discovered at the edge of the solar system connects to something much larger. Something that affects not just distant spacecraft, but Earth itself. One of the most important roles of the heliosphere is protection. The solar wind and the sun's magnetic field act as a kind of shield, reducing the number of cosmic rays that reach the inner solar system. These cosmic rays are not harmless. They are high-energy particles that can interact with Earth's atmosphere, creating cascades of secondary particles. They can affect electronics, influence biological systems, even play a role, subtly over long periods, in atmospheric chemistry. By shaping how many cosmic rays reach Earth, the heliosphere influences our environment. And Voyager showed us that this shield is not constant. Its size changes. Its shape shifts. Its effectiveness varies depending on conditions in both the solar system and the interstellar medium. This means that Earth's exposure to cosmic radiation may have changed over time, not just because of solar activity, but because of the environment through which our solar system moves. Because the sun is not stationary. It travels through the galaxy, and as it moves, it passes through different regions of interstellar space. Some regions are denser, some are more rarefied. Some have stronger magnetic fields, others are weaker. Each of these environments can compress or expand the heliosphere, changing how well it shields the planets within. In other words, the boundary Voyager crossed is not just a distant curiosity. It is part of a larger system that connects the Sun, the galaxy, and Earth itself. A system that evolves over time. A system that we are still learning to understand. And this leads to a broader realization. If our models of something as close as the edge of the solar system needed revision, what about the models we have for more distant regions? For other star systems? For the interstellar medium across the galaxy? For the structure of the Milky Way itself? Voyager reminds us that every model, no matter how carefully constructed, is incomplete. Not because it is flawed, but because reality is richer than our descriptions, more detailed, more nuanced, more complex than we can fully capture at once. And that is not a limitation of science. It is the reason science continues. Because there is always more to discover, always another layer to uncover, always another question to ask. In this sense, Voyager's journey is not just a physical exploration. It is a philosophical one. It shows us how knowledge grows, how certainty gives way to curiosity, how understanding deepens over time. And as we return to the question at the heart of this video, how long it would take humanity to travel 1 light-year, we begin to see that the challenge is not only technological, it is conceptual. Because before we can travel those distances, we must understand the environments we will move through. We must refine our models, test our assumptions, and be prepared for the possibility that reality will surprise us again and again. Because the universe does not conform to our expectations. It reveals itself gradually, and often only when we go far enough to see it directly. Voyager did that. It went farther than anything before it, and in doing so, it showed us that even our most confident predictions can be incomplete, not wrong, but unfinished. And that may be the most important lesson of all. Science is not about being certain. It is about being willing to revise what we think we know, to follow the data, to accept that understanding is always evolving, and to keep asking questions, even when the answers become more complex. Because that complexity is not a problem to solve. It is a reality to explore. And in that exploration, we come closer to understanding not just the universe, but our place within it. Voyager did not give us final answers. It gave us better questions. And after all the data, all the discoveries, all the corrections and refinements, it leaves us with something deeper than numbers or models. It leaves us with perspective. A reminder that even at the edge of our own solar system, there is still so much we do not fully understand. And that understanding grows, not by avoiding uncertainty, but by moving toward it. And after all the data, Voyager leaves us with something even deeper, far beyond the planets, beyond the last faint glow of reflected sunlight. Two small machines continue their journey. They no longer take pictures. They no longer fly past worlds or capture dramatic moments. There are no storms to observe, no rings to map, no moons rising over alien horizons. There is only darkness, and within that darkness, motion. Voyager 1 and Voyager 2 are still moving, slowly, steadily, almost silently, drifting farther into interstellar space with each passing second. They are now so distant that the sun, the star that once dominated their sky, has faded into just another point of light among billions. If you were standing there, beside them, you would not see a bright solar system behind you. You would see stars in every direction. The sun would be one of them, nothing more. And yet, even at this distance, even after nearly half a century, these spacecraft are not entirely alone. They are still speaking. Their signals, weak, fragile, almost impossibly faint, continue to travel across billions of miles, carrying with them the last active connection between humanity and the space beyond our solar system. It takes more than a day for those signals to reach Earth. By the time they arrive, they are barely distinguishable from the background noise of the universe itself. And still, we listen. We listen because those signals represent something more than data. They represent continuity. A thread stretched across unimaginable distance, connecting our world to the farthest place we have ever reached. There is something deeply human about that, because Voyager was never meant to last this long. It was never designed to become an interstellar mission. It was not built to explore the space between stars. And yet, it did. Not because it was perfect, not because it was powerful, but because it endured, because it kept going. Because long after its original purpose had been fulfilled, it continued to drift outward, carrying with it the quiet persistence of human curiosity. In many ways, Voyager is not just a spacecraft. It is a reflection of how we explore. We do not begin with certainty. We begin with questions. We build what we can with what we have, and we send it into the unknown. And sometimes, if we are fortunate, it goes farther than we ever expected. Far enough to change how we see the universe. Far enough to change how we see ourselves. Because when Voyager crossed the heliopause, It did more than leave the solar system. It crossed a conceptual boundary. For the first time in history, something built by human hands entered the space between the stars. Not in theory, not in imagination, but in reality. And that matters. Because when we talk about traveling 1 light year, about sending humans or machines across distances so vast they stretch beyond comprehension, we are not starting from zero. We have already begun, in the smallest possible way, with machines that move slowly by cosmic standards, with signals that fade as they travel, with journeys that take decades just to reach the edge of our own solar system. But still, we have begun. And Voyager stands at that beginning, a marker, a first step, a reminder that even the longest journeys start with something small. It is easy to look at Voyager's distance, billions of miles, and think of it as enormous. And it is. But in the scale of a light year, it is almost nothing. 1 light year is about 5.9 trillion miles. Voyager has traveled only a tiny fraction of that distance, a fraction of a fraction. And yet, what it has already revealed is immense. It has shown us that the boundary of our solar system is not simple, that interstellar space is not empty, that the universe does not always behave in ways we expect, and perhaps most importantly, it has shown us that exploration is not about reaching the end. It is about extending the edge, pushing it outward, one discovery at a time. As Voyager continues its journey, there will come a moment, inevitable, quiet, and final, when its power will run out. The instruments will shut down. The transmitter will fall silent. And the faint signal that has traveled for decades will disappear into the background of the universe. No more data, no more communication. Just 2 small objects drifting endlessly through interstellar space. They will continue to move, they will continue to exist, but they will no longer speak. And yet, their journey will not end, because even in silence they will carry something with them, a record, a message, a reminder that once, on a small planet orbiting an ordinary star, a species looked outward and decided to explore. There is something humbling about that. We often think of ourselves as central, as significant, as the focus of our own story. But Voyager tells a different story. It shows us how small we are and how far we can reach, how limited we are and how persistent we can be, how little we understand and how deeply we want to know. Curiosity, persistence, humility. These are the qualities Voyager carries into interstellar space, not as words, but as action, as motion, as a journey that continues long after the reasons for it have faded. And perhaps that is why Voyager matters, not because of where it is, but because of what it represents. Because in the vastness of the universe, where distances are measured in light years and time stretches across billions of years, even a small step can be meaningful. Even a slow journey can be profound. Even a faint signal can carry significance. And as we return to the question that brought us here, how long it would take humanity to travel 1 light year, we begin to see that the answer is not just about speed. It is about endurance. It is about understanding. It is about the willingness to move forward, even when the destination lies far beyond our current reach. Because 1 light year is not just a distance, it is a threshold, a measure of how far we have yet to go, and how far we have already come. Voyager has shown us the first step, and in doing so, it has revealed something both simple and profound. The universe is vast, but it is not unreachable. Not completely. Not forever. The Voyagers will one day fall silent, but the boundary they crossed will remain. A reminder that even our own cosmic neighborhood is more mysterious than we ever imagined. And as those 2 machines continue their silent journey into the dark, they leave behind more than data. They leave behind a question. If this is only the beginning, how far might we one day go? And perhaps more importantly, what will we discover when we get there?